So welcome back, geometers. We've had a couple days of algebra review stuff. What's the F word that we've been working with? Factor. Do you guys feel okay at factoring right now? Like maybe not perfect. Hopefully you feel better now than you did 3 days ago when we saw the first one. We will do that again, I assure you. Okay, today in class, however, we are going to start looking at chapter 4. I can probably unfreeze that. All right. So, thank you, Liam. Chapter 4 for the next however many sections, and we can look at this. Chapter 4 focuses on one big overarching idea. And all of this, and I'll actually use the word, you guys can draw a triangle if you want. Our entire focus throughout this chapter is back to proof stuff, first of all, but we are only going to be looking at proofs with triangle congruence. Okay, that is our whole overarching focus for this chapter. Now, in 4.1 specifically, we'll see some triangle stuff, and realistically, I normally use triangles because they only have 3 sides compared with bigger shapes that need more drawing. Okay, 4.1, instead of looking specifically at triangles, we're just looking at the general idea of congruence. Now, because it's the same name as the first topic header, I'm just going to go ahead and write it here, congruence. And I'm writing it in all caps to indicate what? Yeah, it's a vocab. Now, we've seen it before. It's not a new vocab, but it is something that we have to make sure we're comfortable with it. First and foremost, is there a shorthand, a real one, that we use to represent congruent? It's an equal sign with a what? It's not a dash. A tilde. Here's equals, which I've been pretty forgiving when we use equals and congruent interchangeably. We're going to start formalizing a little bit more. Equal just means the lengths or the measured angles are the same. So 10 inches and 10 inches, or 3 feet and 3 feet. Those are both equal. Now, if I just say something is like conceptually the same size, and I don't really care about its actual length, just saying it's the exact same size as this other thing of the same type, we use this symbol, congruent. Now, realistically, what we see here is just a combination. We know what equals means, same. This shape here, the tilde, it does stand alone also. It just means similar. So same shape is all that one means. Equal means same size. You put them together and you get same shape, same size. Cool. So looking at this, just as a recall type idea, all that this means, and I'm going to stick with that one, same shape, same size. That's what it means for two figures to be congruent to each other. Exact same shape, exact same size. Now, coincidentally, all throughout chapter 3, we looked at rigid transforms, right? And we looked at 3 of them. What were they again? Perfect. Like zombies, translate, rotate, reflect. And everybody says them in a different order. That's cool. In any of those situations, did we ever change the size? Which meant whatever we started with and ended with, were they the same shape? Were they the same size? So in reality, not only were we just dealing with rigid motions, but we were dealing with figures that were what? Congruent. We've been dealing with congruent stuff throughout the whole last chapter. Now, just so that you guys have it, we talked chapter 3 was rigid motions. Can you give me another word that we regularly use to discuss rigid motion? A rigid transformation was another one. Is there a fancier math sounding word? An isometry. So just so that we can see it, turns out we've really been doing all of this all along. When we look at these, another phrasing that we could have used, just so we can see it, is we had rigid motions or isometries, whichever one you'd rather write. These things, transformations, reflections, and rotations, are often called something else. Now, isometry is the best word for it. Like, that is the real true math word. But when we look at it in the lens of geometry, as first year geometry students, rigid motions, we oftentimes call them congruence transforms. And as long as we all agree that congruent just means same shape, same size, and every translation, rotation, and reflection that we did led to something the same shape and same size, I think it's reasonable that one might have called these congruence transforms instead. Do you guys agree that that's a pretty natural choice? We're transforming or moving it, and it's still congruent. Okay, That's all out of the way. Now, as we look at congruence, there's a couple different ways that we can define this. Same shape, same size works perfectly. Now, what I want to dig into is what does that really mean? And if we wanted to, and whether you want to or not, we will be proving that things are congruent. Unfortunately, it can be kind of a challenge to prove that. Now, we're going to work out and practice because we haven't done proofs throughout all the last chapter. Like, we'll review it, we'll go over it, we'll build it up. I'm still okay. Remember, if you don't completely get proofs right now, that's okay. We have all year to do it. Sweet. As we're looking at these, if we have congruence, we can call them transforms. We're going to look at specifically congruent figures. And I'm going to sneak it in congruent figures. Now, if I gave you two triangles, Sevilla, and I said, hey, determine if these things are congruent or not, how would we even start to think about even showing that two concrete triangles are the same? So that they're both triangles. Cool. So you could check perimeter. Can two triangles have the same perimeter if they're different? I think so, probably. Angles and lengths, something there. Now, do we have a way to check the distance between 2 points? So you could use Pythagorean theorem, or you could use the more streamlined version of formula that we worked out. You could use a distance formula. You could check a bunch of lengths, right? And that's kind of tedious. Here's the harder part. Have you ever solved for an angle? I don't think so. We've measured angles briefly with the protractor, but if I said, here's a triangle without any general measurement and said, find me the angle, you've never done that. You might have done a little bit of it in physical science if you had Miss Forfietta, but most of you had me, and I don't think we've ever done that. Okay, so there's an issue with it. Now, the good news or bad news is your book approaches this very different than I would, and because of that, we're just going to gloss it over because I care way more about the math, like the true math, the nitty-gritty part of geometry, than I do about this other part, but we need to see it. To show that two figures are congruent is an easy way to define this, and it's not quite a definition, but if we want right now to show that two figures are the exact same shape and the exact same size, what do we do with our bell ringer? We sketched it, and we showed that there was a single rigid transform mapping one from the other, or to the other, right? Does that verify exact same shape and exact same size? Yeah, like we saw that up on the board. It lined up perfectly. So for now, without the fancy proof stuff, when we look at congruent figures, all that we have to work with at this point in time is, does there exist, or is there, rather, is there a rigid transform between them? Now, it could be multiple of them, like we saw today. If we can identify a single or composition of rigid transforms to get from one figure to the next, we guarantee they're the same shape and same size, and therefore they are congruent. Is there a rigid transform between them? Now, for this class, and I'll tell you, I've never taught congruence with rigid transforms before. It seems reasonable, we can do it, but there is much better way than saying sketch it, play around with the wax paper, let's find it. It's nice and it's doable and it's accessible, but we've just spent a whole chapter doing that. Like, I don't think we need to spend a ton of time on that. We'll look at a couple of them. We've actually did the one example that I was going to do today as our bell ringer, so that's pretty sweet. We're going to go ahead and branch out a little bit. When we're talking about congruent figures, if I have a bunch of triangles drawn and I say this triangle is the same as this one, we need to be able to write that down and be really clear with what it is that we're writing. So this word or this vocab, and there's a bunch of it because we're at the start of a chapter, we're going to define for ourselves a congruence statement. Now, I don't believe that this is the exact language that your book uses, but I guarantee any chapter moving forward from now on where I say, are these congruent? I'm going to expect you to be able to write the congruent statement, to be able to identify it, and to be able to write it correctly. Like, you're going to keep seeing this more than just chapter 4. Okay, what do you think a congruence statement might be? It could be a formula. I'm okay with that. It's not going to look quite like a formula, but all that we're looking for with our congruent statement is it tells how the mapping between congruent figures works. Shows how the mapping between figures works. Now, this is different than like the formula, the vectors and stuff that we did before. I'm not really looking, is it a reflection, is it a rotation? That was just a way to check to see if stuff was congruent. We are going to look at how a mapping actually happens. Now, we could do this with a 5-gon or a 6-gon or a 7-gon if you want to do it with 7 points. Or what's the easiest polygon that we could possibly work with? Let's use a triangle. So we're going to look at an example of this, and I'm going to help us out, and we're going to talk about it for a minute. If I'm going way too slow, what do you do? You tell me. If I'm going way too fast, what do you do? Tell me. I have a brain break for us today if you'd like to talk about some weird stuff. It's biology kind of related, but we'll get there. Okay, check it out. Let's look at a congruent statement. Let's say I have triangle ABC, and I'm going to make the claim that this is congruent to triangle XYZ. Okay. Now, if this were in fact true, first thing I'm going to do, you're not going to change yours, but I'm going to change mine. Can you name triangle ABC differently? Could I call it CBA if I wanted? Yeah, and could I change this one's name? So if this statement is true, hypothetically, don't change yours, but I just want to know something. Like, I know I hit all 3 points. If that first statement is true, don't change yours. Is this statement also true? Yeah. Like, this triangle is still the same size as this triangle, right? But it's not quite true anymore. And there's a reason it's not true. When we go in a particular order, do you think that that is specific? Very much so. Right away, the big little sign I want you to make is right here, we're going to say order matters. Now, this is kind of a double-edged sword because order does matter in the same sense that order matters with slope. You have to be consistent, right? y2 minus y1, you would use x2 minus x1 if you're doing slope. But you could do y1 minus y2, and then you'd have to do x1 minus x2 in the denominator. We've seen order matter already with slope and stuff. The same thing is true. Realistically, this order, ABC, doesn't matter. But the second we write one triangle, the other one has to match. Now, when we're looking at this, this is an example of a congruent statement. And one more time, congruent means what? Same shape, same size. It means all the side lengths are the same. They have to be. But there's 3 other things in a triangle that must be the same. All the angles. If we wanted to be wordier, we could say all angles and all sides match, right? Like 1 to 1, they're perfect. When we look at this order, crazy important. I want us to draw the following. And I'm not going to change. Well, I'll use blue. That's fine. We don't need graph paper, huh? Okay. Let's hold on 1 second. Okay. Based on what I've just drawn, does angle A, and I'm just going to write implies, and I'm going to go downward. We don't normally go that direction. But does angle A on our first triangle match up with another angle on the second? That order is specific. When we write this congruent statement, it means angle A is congruent to angle X. If I wanted to use equal instead of congruent, what else would I have to have? The measure. I'm going to start being crazier. We'll ease into it, but we're going to start using equal and congruent appropriately. Okay, can you give me another pair of angles? B, guaranteed, is in line with what? Y. Why? How would you explain that rule? Because I agree. How did you know it was B and Y? Middle to middle, right? First to first, middle to middle, angle B and angle Y. Is there another congruent pair there, Kevin? Good. And if we're looking, here's how I would suggest, and this is how I do it every year. They match up, right? Last to last. Now, Ronaldo, you asked a interesting question. I just didn't quite hear it. You said what triangle? CBA, it goes CBA, 3, 2, 1. Is that ZYX here? Yeah. We could write it that way. Absolutely. Yes. You're stretching. Okay. Now, right now, we just have all the side lengths are the same, which maybe that will ultimately mean something, but I get more than just that. Sorry, all the angles are the same. Cool. Does this mean that they're the same shape, same size? I don't think so. Why not? So the angles all match. If I have two triangles and all the angles match, must they be the same size? Why not? I think you can. Yeah. This triangle exists, right? Does this triangle also exist? I wouldn't draw this one. Are these the same shape? If I did it perfectly. Means this angle and that angle matches, right? Does just angles being the same guarantee the sizes? So we have all the angles, that's awesome, but that doesn't guarantee congruence. What else must be the same? The sides. Now, here's the cool thing. As long as you write these in the correct order, you're going to be fine with it. When I look at this, this will be hopefully the only time that we have to write all of these, but we'll see if that really holds true. If I select this segment, that's first and second, right? Segment AB happens to just perfectly align with which segment on the other triangle? XY. Boom. I legitimately think this will be the only time we write all of these. Give me another segment that you guarantee is the same. BC must be the same as what, Klein? Okay. Do you understand why that's the answer, other than it was whispered? Like for real, like I'm not trying to bully you. I'm not picking on you. Like I would rather you guys don't sleep. I get that you have your stuff going on and that there's participation grade. Just throwing it out there. Do you know why we said YZ? Because I really care about the math more than I care about your sleep, to be honest. That's not true. That's not a fair statement. Good. BC is second and third. What's second and third? Good. There it is. Okay. One more if we look at this. Ryleno, if I said CA, and I can't just draw the lines anymore, I usually do this, CA. ZX, boom. If you have the order of this statement written and it's correct, it is so easy to pick apart all these pieces. Now, you could, absolutely. If you went AC, how would you write the other segment? AC would be XZ, and we just changed the order. Now, doesn't matter, as long as it's consistent. Cool. As we go through this, this is really and truly what it means to show that something's here. Now, there are two routes that we can go when we're trying to really determine if two things are congruent or not. Would you like a quick brain break first? Okay. We've already said that things being congruent just means same shape, same size. And for now, at least, all we can do is say, is there a rigid transform between them? Okay. I'm not going to give you guys an assignment tonight. We'll probably only do a few short problems from this section in reality, because we could look and look and look and keep working with rigid transforms, but we just did a whole chapter of that. And reminder, if your quiz or test didn't go really well, the option there is to retake it still. No missing work and reflections. If you get both those things done, we can retake the test for up to a 90%. Okay, as we go through here, we're just going to look at a couple of these really briefly, and we don't have a ton more to deal with regarding this, but let's check. We're just going to look at a few together. You don't have to sketch them and stuff because we just have the examples in the text, and if you want to see them, it's all throughout, but here we go. My first thought is, without being able to just blindly trace it and stuff, are these congruent? Why? It looks like a reflection over the y-axis if we had it. Okay. Or it could be a rotation by one. Nope. 180, this point would wind up here. 270. So you're talking about just rotating it and then translating? That would work. 270 would do it. Cool. There's realistically probably a 270 somewhere up here where if we spun it, it would land back on itself over here. Like, I'm fine with that. Okay. How about this one? No. Why? Because the one's thicker than the other. And we got to focus so you can actually see it. The first one's thicker than the second one. There we go. They're different frames, right? Yeah. They're kind of the same size-ish, lengthwise at least, but definitely not the same size in the other dimension. Cool. Now, they're same shape, different size because of that depth or thickness. Cool. How about these two? No. Okay, this one's tough This figure, we need this box to wind up down here, right? If we flip it like this, it's going to be the wrong direction, but if we rotate it again, I think we're going to be okay. Yep, they can be tough to see. Now, with these, let's see, is there a pair between these guys? If we rotate 90, does it look like it? This one looks different to me, and I don't know why. I'm not. The color change might happen, so definitely it is rotated. I think it's reasonable to say probably they are the same. Okay, it's hard for me to see without wax paper or tracing paper and actually seeing it. We can't be 100% certain, but it looks reasonable that it would simply rotate. How about these?
No.
No, and that one's much easier, right? Okay, as we go through here, I don't. Here's where I need your guys' help with stuff. Do you feel, and you can just thumbs up, thumbs down, do you want to do congruence with rigid transforms like we did throughout chapter 3, or do you just want to move on to doing it without needing to actually draw and trace? Anybody just dying to do more rigid transforms with reflections or anything? We can either try to show stuff as congruent using those, which we've looked at, and we did one today for a bell ringer without any instruction. You've already done what this section is asking. Or we can just say we're really going to buckle down and do the math and see that there's better, more efficient ways without having to draw and trace. Cool. So for today, this is going to be, I don't think I'll have another section where this happens. I think that this is legitimately going to be the only section. There's not a homework assignment for this section. Cool. I think I've said all that I'm going to say about this. Tomorrow, bring your proof hat. Cool. All right. Real quickly, if your